Hey everyone, so I have a fun little topic for you titled AWS Lambdas are cool for cheminformatics and chemical toolkit usage. So this is a topic that we are very passionate about and we are sharing it so that you can pick up the technology and perhaps enjoy the same benefits that we do. So first a little bit of an introduction. Perhaps not all of you know what a Lambda function is. So it's a piece of serverless technology that most of the cloud service providers now have. That includes AWS and Microsoft Azure and Google Compute Engine. Serverless means that an application developer doesn't need to bother with creating servers where you kind of log in and install applications. Essentially, you package up your application into a single zip file, which, when needed, is automatically deployed to a worker instance. On this worker instance, your function call can take approximately 15 minutes, and you get a single CPU core and a max of 3 gigabytes of memory. This varies a little bit between providers, but this is a good number for us for the purpose of this exercise. When your function is not needed, roughly after 10 minutes, it is stopped and discarded. The good thing is that if there are parallel incoming requests, you automatically get 1,000 parallel executors, no questions asked. If you talk to support, you can even get higher allowances. So this all seems to be really ideal for jobs where the demand or load widely fluctuates. For instance, because it's based on human interaction. Also, when your job is made up of small pieces that fit into the kind of hardware limitations. By default, there is support for Java, Node.js, Python, Ruby, Go, and C# runtimes. However, there are a few catches. So one is that, at least at AWS today, the maximum deployment size for your zip file is 50 megs. And this needs to include things like an SDK. Then, because your application is only started up when it's needed, there is a delay. Literature calls this a cold start. And we also observe something like a secondary cold start, which I will talk about a bit later. And finally, the costs can be up to 48 $micro a second or $4 a day, which compared to equivalent on-demand hardware, it seems a little bit high. So a T2 small instance, reserved instance, can be as low as $156. So this feels like it's 10 times cheaper. So we like it because the advertisement says that it's, it can be beneficial for software architecture, but there are a couple of catches that we need to investigate to find out if we can actually use this. Now on to how or where can we use this technology. So I took my application, Design Hub, and here is a little bit of a chart that shows its architecture. So we have like a web server, we have a SQL database, we have an identity provider, a log server, the usual stuff. And we have plugins over on the bottom left, which are small pieces of functions that do calculations and things like that and connect us to a computational chemistry infrastructure, including cheminformatics and models and predictions and machine learning. On a screenshot, I'm looking at a compound, and there's like 15 or 16 tools, each a plugin, as we call them, that describe that compound for me from a certain topic. So I apply a little bit of a highlight to show you that these are the ones that I think Lambda technology could be applied for, because these are the ones that use on average 1 or even less CPU, around 300 or 400 megs of RAM, and takes just a few seconds to calculate these. The rest are big database searches and complex applications that obviously don't fit into these limitations. So what we can say is that in roughly 2/3 of the plugins that we do are possible with the Lambda implementation. And in terms of like the absolute number, if I take a look at an example, about 150 chemists would make 2 million plugin calls in a year. 25 chemists might make about 400,000 plugin calls in a year, and like 5 chemists at a small organization might make a couple thousand plugin calls in a year. So if we can get our Lambda technology to work on like the million scale in a reasonable manner, then we have a really, really nice solution on our hands. So what I'm saying is that 1 million plugin calls would be a lot. So now let's look at the 3 problems. The first one is the deployment size. So on the left, what you can see is a description of our Gradle dependencies, which is fairly typical for most Java applications. We have our implementation, a sample plugin, conformer generator plugin, that needs about 12 kilobytes on the disk. Then we have the AWS SDK, which is about 8 megs. Finally, we have JChem, which is a lot. However, if we exclude things that we certainly don't need, like the Marvin editor and database drivers, then we can get it down to 60 megs, kind of easily actually. However, our total is still way over the advertised limitation. The solution turns out it's a little bit hidden, but once you find it, it looks kind of obvious. So when you try to upload your function, there is this little upload tool, and it gives you a hint that for files larger than 10 megs, consider uploading using Amazon S3. So we did that, and it turns out that if you do that, actually the limitation is 250 megabytes, and you can still deploy from S3. So that's actually the very, very simple solution. First upload to S3, because then the limitation is very different. It's 250 megs. And this is okay. So this is not a hack or a workaround. The FAQ even says that for security reasons and others, when you upload a small package, that's what Amazon does anyway. They store your code in Amazon S3. So this is fine. It's that simple. Now let's look at problem number 2, which is a startup delay. So we did a series of tests to figure out how big of a delay it is actually. At random times, we made a batch of calculations and looked at what delay we observe related to the first call in that batch, and the second, and the third, and the fourth. With the first ones, but this is the kind of 5-second delay that we see. So this is the time when from like an unused instance state, our zip file is copied from storage to an available worker instance, and our Java virtual machine starts. On the second calculations, what we see is basically the effect of the Java optimizer, where functions that enjoy repeated use get further optimized. So this is the just-in-time optimizer of the JVM. This costs maybe an extra second. We see a little bit of an effect on third calculations in the batch, but from that point, it's very, very negligible. There is continual optimization for a while. So this is the startup delay. So obviously we don't really like the 3-4 seconds and like the 1 second that is here. And all of this arises from the fact that when our instance is not used, it is dropped. So what can we do about this? It can be as simple as creating a script that basically keeps our instance warm, which means that we don't let a 10-minute idle period to happen. So for instance, if we know when there are logged in users in our applications, which we can generally expect in office hours, or when there is no activity just yet, but can be expected because people navigated to a screen that has a bunch of functions related to Lambda usage, then we run this script. At worst, this could be something like pinging our Lambda function every 10 minutes, like 48 times a day with a dummy package, like a carbon atom or something like that. And we did cost analysis on this, and the cost is around $1 per year per plugin instance. So it's a relatively simple addition to our costs. But the good news is that we don't even need to do this script, because very, very recently, Amazon introduced a new option for the management of Lambda functions called provisioned concurrency, which actually deals with the cold start effect in the same way that I described, and you can configure this on the user interface. You can configure time intervals when you need a number of available warm instances. So this is a great solution for anybody who uses Java in their Lambda functions. Finally, let's look at problem number 3, which could be about cost, but also performance is somehow related to that. So we did one plugin implementation a couple of months ago, which does conformer sampling. We grabbed 1 million random molecules to run tests with. And to set a baseline, we did a local test where we configured the application to use just one CPU core and 3 gigabytes of memory. And essentially, the average performance that we got out of this was around 200 milliseconds. So when we run the same test on AWS and we configure it to around 2 gigabytes of memory, then our average build duration was 230 milliseconds. So what we can say from this is that Amazon has very, very similar CPU cores that we do in our development machines. And for the same hardware, we get essentially the same performance within 10 or 15 percentages. So that's fine. But the cost is really nice. So that's what caught us by surprise. On the vertical axis on this screenshot from the Amazon Cost Explorer, you can see dollar amounts. So when we were running one of the tests with 1 million compounds, then it turns out that our cost was 21 cents. This included a bit of free tier. Without free tier, we estimate that our costs would have been close to $7. But free tier is available to everybody, and it's a huge amount, actually. It's like 400,000 calculations every month. So this is something to keep in mind. Obviously, 21 cents is an unbelievably low number, but so would be $7. As a reference, the reserved instance would be $156, and the theoretical maximum cost for a Lambda would be $4 a day. But putting together these numbers, provisioned concurrency or our script would be about $1 a year per plugin instance. Then we might pay up to $7 for 1 million executions. And keep in mind, 1 million plugin calls is a lot. It would serve 150 chemists for a half a year. And finally, there might be additional costs, the largest of which is about 20 cents for HTTP requests coming in through the API gateway. So it's not like this is 10 times more expensive than a reserved instance. This is 20 times cheaper. So in summary, we know of 3 obvious problems, but these are not going to be problems if you follow the tips and tricks that I suggested. I also showed you how you can use Chemexon toolkits with ease in Lambda functions. And as we improve on the technology, this is just going to get easier for everybody. The slow start, which is the largest problem of them all because of Java, is trivial to manage with or without the help of provisioned concurrency configuration. It looks to be very, very cheap to operate. And this is beneficial for software architecture, especially scalability. So not having to worry about servers and getting the option of scaling with demand is huge when we are dealing with interactive applications. There might be remaining problems. So I leave with this question, whether you know of anything else we would be happy to look at this. As I said in the beginning, we are very passionate about this technology, and we would like to continue exploring this and bring a lot of Lambda functions to productions. So find me in the Q&A section, and then we can talk. Back to you, Yonchi.